So this is problem 23-32. What do we have is we have a rod that has a charge, Q, for the total length. So we assume that it's equally distributed, so there's the charge per unit length is Q divided by 2L. L is the distance from the center to the end. We look at this differential element on the rod, and it has a charge dq, and that's equal to, dq is equal to the total charge, q, divided by 2L times d, so that's the charge per unit length, and you multiply that by dx to get the dq. And what we're looking for is what is the voltage at any point along this center line. So it's equally, this y-axis is right at the center of this rod. So it's a symmetric situation. Now, so what we're going to do is we're going to find the voltage due to this infinitesimal charge, and then we're going to add them all up from here to there. So this will be x equals negative L, and this will be x equals positive L. So those are going to be our limits of integration. Now, this is the equation for the voltage is equal to 1 over 4 pi epsilon 0. Remember, 1 over 4 pi epsilon 0 is K. In algebra-based physics, we say voltage is equal to K times Q over R. So what we do here is K is 1 over 4 pi epsilon 0. And we have this dq, which is this differential charge, and we have the distance from that to the point of interest, which is y. So this distance here varies. It's the greatest distance from here to here, and it's the shortest distance from there to there. And using the Pythagorean theorem, the distance, straight line distance from the differential charge to the point y is going to be equal to, which we're going to call r. R squared is equal to x squared, this distance, plus y squared. Now y is a constant for each calculation. If I change y to this, then I get a different voltage. But again, we can consider y to be a constant, and the variable that we're integrating with respect to is x. So for dq, we can substitute in the total charge for the entire length of the rod divided by the length of the rod. So that's dq. For r, we can put in x squared plus y squared. So this integral, 1 over 4 pi epsilon 0, we integrate from negative L to positive L. dq is q over 2L, so that part is dq, and this part is r. Now y is considered a constant, L is a constant, Q is a constant for each calculation. So we can take those three things outside. We can't take the x out because it's grouped with the y squared in this square root. So once you've taken Q over 2L out, you have that. And this is our integral. Now it turns out this integral can be solved using hyperbolic functions, and it's chapter 5. Section 7 or 8 or something like that in the book. But there is an equation that's in the book that looks like this. The integral of 1 over u squared plus a squared d, I guess that should be du, is equal to the natural log of u plus the square root of u squared plus a squared, close parenthesis, and we add arbitrary constant. So that's the indefinite integral. So what we can do is we can fit it into this form. So u is the variable. So u is x. A is y. So we're going to have the natural log of x plus the square root of x squared plus y squared. So using this out of the calculus book, I get that. Where I substitute for u, I put in x. For a, I put in y. Since this is an indefinite integral, but this is a definite integral, we don't add the arbitrary constant c. We integrate from negative L to positive L. So we substitute in the upper limit, subtract the function evaluated at the lower limit, so we have negative L for that. Now the reason this is not, this actually officially is negative L quantity squared, but negative L quantity squared is the same as L squared, so I just put L squared in there. Now here we have the natural log of something minus the natural log of something. So the laws of logarithms say that if you have a difference of logarithms, it's the same as the quotient, logarithm of the quotient. So this is my numerator, this is my denominator, and I end up with this simplified version. And that is it. Now one thing I thought about was, what if I integrated from 0 to L? Because of the symmetry of this problem, if I calculate the voltage here due to this half, could I just double it and do the other half? And the answer should be yes. I have not verified it. So what would happen there is the lower limit would become 0. And then we'd have 2. We'd have to multiply the whole thing times 2 to double it. And I think this, should be some way to prove that that's true, but I don't know exactly what we would do there. So that's left for people. You always say that when you figure nobody's going to do it, we'll leave that up to the student to look at later. Okay, so that's the second problem.